All right. Welcome. Can you hear me all right? Yep. Cool. Hey, I'm Tony Albrecht, and I'll be talking to you today about refactoring League's particle system. When the call for topics came out, I thought this would be a great one to talk about because I just started working on the actual refactoring. We're not finished yet. So hence part one. So hopefully next year what will happen is I can talk about what went right and what went wrong. So we're partway through and I'll be talking about what's happened so far. And it's it's kind of like a journey of the process of doing this particular thing. I think there's some really good takeaways for younger engineers on some of the design processes and stuff. I think it's interesting, dealing with ancient software. It's 10, 15 years old now, League, about 15 years. So dealing with old code. And the other interesting thing is that a lot of the code that I'm modifying is code that I wrote 10 years ago. So I know who to blame. But even that was building on top of existing code that was there by who knows. Our revision control system only goes back to about 2013. That's where we started using per4. So everything before that is lost to the mists of time. The other thing is, there's not just me doing this. We've got a couple of other engineers working on different parts of this refactoring, and a tech lead as well that's keeping an eye on all of this. So. First thing we'll start with is nomenclature. VFX is basically visual effects. It's primarily particles that we'll be dealing with here. The particles are moving elements. It's either quads, trails, meshes, which update according to physics, animation, connected meshes, or all of the above. Emitters. We call the source of particle emission, so it can contain one or many particles. It defines the behaviour of the particles, basically. The instance is a single emitter. Emitters can be reused many times at the same time or different times. For instance, multiple instances of fires. That'd be the same data information as an emitter, but there'd be multiple instances of those, and they'll all appear different. And a group emitter or group instance is a collection of emitters, usually for some complicated ability or effect. Hate that. Let's do this instead. Next. Why are you not going? Oh, here we go. Particles in League. Functionality, we have quads, we have meshes, we have trails, we have beams, we have basic material support in the existing system. I'll call the existing system, or the old system, the monolithic system, and for reasons that will become obvious later. Very little shader support. We have only two types of shaders at the moment that are being used for particles. One is lit, the other is not lit. But we are improved. We will need to improve that because it makes our artists angry. Now it can change behaviour on emitter death. So when it dies, other things happen. Need to be able to handle that. And particles can also be emitted on particle death. So there's a reasonable amount of functionality there. Emitters can be attached to other meshes, animated skins, or other emitters. So there's lots of things that you can do with these things. Simulation is parallelized. This is something that I did 10 plus years ago when I first started at Riot, was to take the existing engine and figure out what I could optimize in it. And one of the slowest things was the particle system. So pulled that completely off the main thread. It's an easy one to parallelize, so that runs very wide on whatever threads you have. It's been optimized many times. With a game that's being constantly released, there is more and more stuff going into it, so you need to optimize it constantly. We're always working on it. And it's heavily abused. The stuff that artists do with the particle system, even though it's quite limited, is amazing. And as an engineer, I think it's our job to make sure that the artists can do what they want, but are also aware of the impact of doing what they want. And that's quite hard. And our current system doesn't give a good indication of relative performance. I did add a little frame rate graph to the editor, but that's useless when you're running on a Threadripper because it's always fast. So the other thing is it must maintain backwards compatibility, right? It has to be 100% exactly the same as the previous. Any changes must remain, like we can't change the particles because if you buy a skin and it has particle effects on it, you can't change that because people have paid for it. It has to look exactly the same. So we'll quickly show some particles. So this is one of our more recent champions. And you can see particles coming at your main character there and actually being reflected back and changing color, which is one of the more recent things we had to introduce. So the ability to do that took a while. We also have things called booms. This is a great example of abuse. It looks great, right? But the way they have to do these things is often quite counterintuitive. So we really want to improve this. So this is a shot from a game from years ago, and there's a lot of particles going on there. Particles are a critical part of gameplay. They signal the beginning of casting of spells, all sorts of information that players need to react to quickly. So it has to be as clear as possible, exactly what's going on. So this is the particles that were in that scene. And that's the wireframe. There's a lot going on. So you're keeping that fast. So currently, in League of Legends, I loaded up just a little test game on my computer and actually put in some counters to see exactly how many emitters we had. There were 21,200 for the random set of champions that I chose. Now, each of those emitters, we don't load during the game. Everything's loaded right up front. So the information for those is being loaded at the start, and that's 24 megs straight up. Now, we have very, what's the word? Our min spec is challenging. We can basically run on the toaster. I reckon most ATMs could run League at a reasonable frame rate. So we have 171 champions. So each of those has their own range of abilities, and each range of abilities has a range of emitters that need to be created for each skin. We have 1,824 skins. So you can see there's a lot of sets of particles. We also have teamfight tactics. That's a bit worse, looking at 35,000, depending on what boards you have and everything. So that's around 40 meg. Peak particle count's about 2,000 emitters on screen, and 10K plus actual particles on screen. So TFT's particularly bad at this. They have all good at it. The stuff looks amazing, but it can really slow down the game when there's a lot going on. But the style of game means that you're not reacting to stuff. It's just eye candy. It's pretty. So it doesn't matter that much. So it's up to the game teams as to what's important to them as far as performance is concerned and how many particles they want. So, and there's about 1.5 million emitters across all game modes. So that's a lot of backwards compatibility that we need to maintain. It's absolutely terrifying. So League has a lot of particles, but League needs lots more particles and better particles. So League needs particles for new champions, for new modes, new skins, and new types of effects. It's bigger, better, and shinier. So, but League's particle system code is 10 plus years old. It was designed to be extensible. You could add new property fields to the emitter definitions. and new code to the particle instance update, and that would work. But it's also, like I said, heavily parallelized. That was once a major bottleneck. But we kept adding new features because we need to. There's more data, more code. It's more harder to understand what the simulation's doing, what the data does. And like I said, backwards compatibility is crucial. So it became harder to add new code-based features to the simulate function due to the backwards compatibility. You couldn't add something in new that would break the old effect, and that was easy to break the old stuff. It's hard to check breakages as well because you've done something, you've tested the thing you've just done, but there's thousands of other particles that do it slightly differently, and that needs to be maintained. The other thing was that emitter definitions hit a max size of about 1.4K each, which is not a lot, but it adds up. And particularly when you're trying to deliver on mobile, 20, 30 meg is a lot. So we worked a lot to reduce those by componentizing related property data. So you'd grab some similar things, create an object, and just have a pointer to that in your data set. So still large amounts of data, but you're not loading everything in all at once. And it helped to kind of understand what was going on. But we're still at around 1,100 bytes per emitter. We've got a static assert in there if it ever gets increased, so that we can't check it in. So, because people don't realise and they break things. This is the emitter definition. The way all our data is stored in JSON blobs, and I've got our own editor that does all of this stuff. So we edit it in this thing here. It's Write Editor. This is Particle Town. So you can see different emitters going across there. They all have different behaviours. You can see the different fields that can be changed there. So it's graphs over time. We've got random values and all sorts of things that you can do. But the large definition data made, excuse me, the large definition data made editing difficult as well, because you've got this massive chunk of stuff that needs to be displayed. So what was done, instead of reducing the size of that, was we actually artificially componentized that stuff at the editor side. So it looks like little components, but underneath it's one big chunk of data. So we've got a maintenance liability there. So any changes to the source need to be reflected within the actual editor, and it's just something you don't really want to do. Okay, so basically we're at this point where it all works, but we need to do more stuff, but the code is so complex, it's ossified, it's become really brittle and hard, and we can't change things easily. So we needed a new VFX system. It must be 100% backwards compatible, must be extensible, must use less memory, must be at least as fast, must be easier to understand. Our artists, they tend to hit it with a stick. Basically, if it's not doing what they want, they keep changing numbers until it does what they want. So it's because it is hard to understand some of the stuff. And some of that is because we have bugs that have been there for 10 years that other particles depend on. So we can't fix them. So it must also work well with our editor. We have to support shaders so that our artists aren't angry anymore. Basically, we need to work better with materials. We need to not break anything. And the game ships every 2 weeks. So how do you design and implement something like that? Who would want to be responsible for that? So how do you start? Well, you need a plan. No plan of operation reaches with any certainty beyond the first encounter with the enemy's main force. Or everyone has a plan until they get punched in the face. So my point is here, we need to have a plan, but you have to be ready to change it even as you learn more. It's a very complex system. We're going to stumble across things that are going to break, and we need to be able to adjust and modify what we're doing so that we end up with a result that works. Step one, figure out what the hell the old monolithic system did. So I spent a lot of time stepping through code, drawing diagrams. I've got pages and pages of notes, just trying to really understand what was going on. And the more I read, the angrier it made me, because so much stuff is done so, well, by necessity, in bad ways, all right? And I'll get into that a bit later. So what we've got here is the data that's generated on the editor side. We have a system definition data, which is a collection of emitter definitions, and those emitter definitions have curves and constant values and random, all sorts of flexibility there, and all need to be able to be these particular types of property data. We generate classes from those that are running in Engine, and they have particle instances, and the particle instances are the runtime particle data, which is a series of arrays of interleaved information. Now, that was something that I worked on 10 years ago as part of the optimization phase, because it used to be just one big, massive chunk of data that was very cache unfriendly. The point here was that per particle you have some arrays, and the data in each of those arrays is being used at a similar time. So then we have the renderer for the emitter. Now, this thing touches everything. It needs to know about, it assumes that there is particular particle data available, and it reaches in and grabs it. It pulls in data from the emitter definition, it pulls in stuff from the instance, it pulls in data from everywhere. That's a code smell. It's tight coupling, it's a leaky abstraction. So code in some classes relying on code and data in other classes explicitly. So there's no clear ownership of functionality or data. This pattern spreads. Once it's doing it, everybody does it by necessity. So if there's no clear owner, then anywhere is fine, right? I can do this thing here or wherever I like. There's no real rules about where things should be. So in addition, we have our particle instance, which has this simulate function, which is called in parallel. And it does every particle's attributes, its position, rotation, scale, color, for every type of particle in 3 massive loops. So it's hundreds and hundreds of lines of code doing a whole lot of matrix maths and interpolations and all sorts of stuff, all interleaved. So any changes to simulation have to be in that function, but you can't break anything in that function, and you can't add any more data, and you can't, it's hard. So the emitter renderer has a large function as well called fill buffers. This is taking the vertex buffers and matrices for rendering every type of particle, basically building up the render data. So it's not sending data directly to the GPU at that point, but it's preparing everything to be sent to the GPU. So these big functions are a code smell. It's a God function. It's a large function with hundreds of thousands of lines of code with too much responsibility. It's hard to understand, it's hard to modify, and it's hard to optimize. Trust me. So this is something, this is a way of passing data into a function that's nice and neat. So it's a single basic container struct, all right? And you pass that into add particle, you can see down the bottom there. And there's 3 structs, not just this one. So there's 20 parameters in that first one. It's hiding the fact that this function's using data from elsewhere. So to call add particles, you need to understand all the parameters that go into it. And it's even doing calculations outside of the generation of that particular struct. So you need to understand what happens inside the function to be able to call it. All right? That's a code smell. So why do programmers do this? Often it's copying what's already there. Somebody else has done it, they will go in and do the similar type of thing because it's okay, you can do it. It's quick, it's easy. Time pressure is a big one. You have tight deadlines, you're just trying to get this thing out the door. So to refactor everything might take months, but I need to get this thing out in 2 days. So you make a quick, simple change and hope that it doesn't break anything. Lack of confidence. Going in and changing this detailed, important system, which is so critical to gameplay, you don't want to break anything, so you just touch it as little as possible. Lack of good examples is, I think, a really good one. If you write it the right way and maintain it, then people see how it should be done. So there's a proper way of dealing with it. So key design elements here, flexibility. Design a system knowing it will change. Like, this is a journey, refactoring this particle system, because we're going to learn stuff along the way. We need to be as flexible as possible, but not too flexible. It's immediacy. What we're doing here is we want to build what we need to solve the problems we have now. Like, no future-proof bullshit, because you don't know how it's going to be used in 5 years' time. You know, it will be different. There is a point where you can look at a system and say, right, that's it. Retire it, burn it to the ground, build something new, and that's okay. Encapsulation it's very important to enforce clear code and data ownership, right? That in itself helps you to write better code. It's harder at first with encapsulation, it slows you down, but in the long term, it gives you more flexibility and more ability to do stuff. And performance, design for it, but don't try and build it optimal to start with, okay? Be aware of what could be an issue with performance, but don't optimize as you go, because you're going to be throwing away code that you just optimized. There's no point. Okay, scope. This refactor is not just what I'm talking about here. We're also building better material shader support, like I mentioned. We're building new and better primitive support. There's 3 of us, like I said, and we're all working closely together and trying not to tread on each other's toes, which is a challenge. And we're also supporting current VFX in the current games, so it's busy. So this is our monolithic system. The first thing we're going to try and do is design a system that provides 100% backwards compatibility. So we'll start with that. We take the data, we extract out parts of that into a chunk, and we build components that are just those things. So we're just moving data from the old system into what will be the new system. And we do that with a number of chunks. So I've chosen 3 here. Render component does rendery stuff like color and things. We have physics, which is like scale and position, orientation, and lifetime stuff with the legacy component for lifetime. So that's all contained in the emitter instance, which is the existing class that we already have. This means we can actually have an array of these components, so we're not having everything in one big struct anymore. It's in a couple of smaller structures. Still the same amount of data, end of the day, but it's a bit more componentized. It's a bit more encapsulated. So doing that, we also then have the runtime, which uses the data from those components. So breaking out code into these structures and these classes was incredibly valuable. I found bugs in our code that's been there for over 10 years. And it's like the reason for why we do that was because that's what we did. There's no logic behind it, but I can't change it because that's what has to happen. So the other thing we need to do is, like, if we're going to break it out into those runtimes, the simulation loop will have to change as well, which is good because we've got this massive, big simulatable particle thing. So we've got a couple of options. We could do, for each particle, call each of the different runtimes and call the simulate on each particle as we go. That's useful because it's exactly the way that the old system did it, but there's function overhead there. So we're calling a lot of potentially virtual functions, and it's probably a bit too branchy for every single particle. So the other option is we can, for each of the components, do all the particles, and that's the one I prefer. That should be faster, but the second option violates order of operations. So is it exactly the same if we're not doing the maths in the same order? Well, that's something we need to figure out. How do we tell that if the legacy components are actually correct? We've changed code, we've changed data. Have we made any mistakes? Are order of operations important? We had one big loop, now we've got a few smaller ones. How can we be sure that our new system is identical to the old monolithic one? Do we eyeball it? Do we just have QA look at 1.5 million particle systems and say, this is exactly the same as the last one? Do we do per pixel comparisons on snapshots of game screens? That was actually one avenue that we were looking at. Do we lie? What I ended up doing as a matter of necessity to prove that the components were working was build a validation pass. So what we do is per emitter, we simulate the old style and we produce the data that comes out that gets fed into the renderer. Then we simulate again exactly the same data and same source and output to a buffer that would go to the renderer. Compare that output data, byte by byte. If they're exactly the same, we have managed to do the legacy simulation correctly. Assert on failure. So I wrote that system. It works. It's great. The problem is that when it asserts, it's some particle in the emitter that's different, and you don't have any logging on. You can't log that many particles. So I ended up building a system that allowed me to unroll logging and actually output information, so I could see when the legacy differed from the monolithic and what it was actually doing in code at that time. So that's being used, but it's a bit slower. I'll get to that in a second. Click, click, click. Here we go. This mostly worked. The problems. Some particle input is random. Random numbers are random. So what I did was I store a seed before doing the simulation, and we use a pseudo-random number generator, so that the same, given a seed, you can guarantee the same order of random numbers. Works as long as the order of calculation is identical. Simulation is multi-threaded, which introduces randomness. So you're not simulating in the same order as you were before. But you can force it to a single thread. It's a little bit slower, but that's okay. But we changed the order of simulation as well. So what do? We can no longer guarantee that random numbers match due to misordering. So here's what I did. So that works. What this means is we can enable multi-threaded simulation again, because the order of the random numbers is not really relevant anymore, so we can get away with stuff. That should be good enough. So validation, so we've got some confidence now that our VFX are correct. Still not 100% coverage, but it's better than lying. Programmers will test specific functionality. You write code, you make sure it works, you do a little bit of checking, and for a programmer's eyes, it works. Artists will test and compare against the monolithic with the new and the old, and they can run them side by side, identical, and they can say, yes, this is doing what it should do. We can run games with validation enabled, so we set up a game, QA can run through it, or we can have bots running through it. We'll limit it just to internal shards. We don't want any of this code going live, and I'll get into that in a minute as well. We can log validation errors with emitter paths, so we know what's broken. We can also keep replays of the game, so that we can then go back and inspect it and see exactly when things went wrong, have more logging on so we can actually find the problems. So how do we release code for internal testing without breaking the game? We do a few things. One of them is if-defs in code, so that doesn't go for live builds, all right? Just the internal stuff. We have flags required to enable components in the editor, so if you want to use the new stuff, you've got to hit a couple of flags in different places to say, yes, I want the new component stuff. We also have validation on saving. If you have used it and you try and save it out to a layer that's going to go to live, it'll tell you, don't do that. We also label stuff in the editor with components do not use, but that's still not enough. We had a crash on internal builds. One of the artists had enabled it, didn't realize that what he was doing was wrong, and it caused a crash. So we had to fix the crash as well as revert back the changes that were made for the particle effects. I broke memory testing because I was jet lagged and stupid. I took out some if-defs that I thought were identical to the ones above it because it was just nested, so I thought, no, that's stupid. But no, they weren't. They looked similar, but they were different, and I turned on components for all of TFT, so memory testing blew up. So let's assume we have backwards compatibility now, right? We have components. We've got these legacy stuff. They are exactly the same. They work. Great. Now what? Let's build some new components. We've got a new awesome render runtime and physics runtime and the lifetime. They're different and there's no bugs in them. But you remember this renderer? It's touching everything, right? That was leaky, and we haven't changed that yet. So what we wanted to do here was make the emitter renderer only go through an interface in the emitter instance. The emitter instance can then decide where the data is querying comes from. It's either from the monolithic stuff or it's from the new components. And for the time being, you can switch those dynamically. So you can have both sets working. We also have the ability in code to force everything to be the components versus the old ones. But the problem here is, where does the particle data live? We had a class before that did that, and I hate it, and I can't wait to delete it. But similarly, these components have access to particle data. Where do they keep it? How do they share it? Like most of the components, they're going to want to have lifetime information. So where does that live? So we made a particle data container that lives at the emitter instance level, and everything registers the types that it wants to use and sticks them in the particle data container. So this particle data container abstracts away the per particle data. It manages memory and alignment, so you can have arrays of data or interleaved data or whatever we want. We have control of it. It does allocations for us, hence the alignment, but that means we can do SIMD if we want to, nice and easy. We've got aligned data. We can define how often we allocate. That was one of our bottlenecks on the monolithic system. So we have an option for SIMD. We're not writing it now. I'm saving that for later. It's like ice cream. I can't wait to do it. And yeah, we should be able to use that in certain components. So basically we have access to this type data kept in one spot. It allows us to have better understanding of exactly how much data is being used, because we can query it and say, okay, what's this data size per particle? It's all kept in one spot. It's a very clean abstraction. So any component at any time can get particle lifetimes or velocity or whatever. It also abstracts away availability. So you can return a default value if it's not there. So if you're trying to get velocity and it doesn't have a velocity, it can give you a 0 back without crashing, theoretically. So, like I said, we made the leaky emitter renderer, get everything from the emitter instance, and the emitter instance decides where the data comes from the data container or the monolithic system. I mentioned that before, which is great for validation too. Because we know where the data is, we can easily do comparisons. Now what? Well, we have legacy components, same functionality, similar memory footprint. What else can we do? Well, we can build new components that are completely different. So first one I built was a basic physics component that just took the very acceleration, velocity, and did some and scale, and that uses a very small amount of data. There's a small amount of code. It's very specialized and it's relatively fast, which is great. The next step was say, okay, well, let's do something really clever, and something I wanted, like was my idea for the initial design, was to be able to have components. So one of the big problems we had before is you can't modify the code that's there because you can't want to break anything. This will allow you to build completely separate modules, the modifiers that fit into the physics runtime. So you add in your core maths and it does the core math stuff. If you want to do rotation, you add one of these and it does rotation. So You want drag, you can put that in there. So whatever you want, you add it, you then pay for the memory. You don't pay for it when you're not using it, and you pay for the cost of simulation at that point as well. So I built one of those out as well. It's flexible, it's extensible, you only pay for what you use, which is great. But update order needs to change. Like, if I have a drag component that affects velocity, then I can't do that after the rotations occurred, because it's going to be doing the wrong thing. So what has to happen here is we need to have phases of update. So we do all the acceleration stuff first. So all the components that have an acceleration update get the acceleration calculated and accelerations updated in the particle data container. Then we can do the same thing with velocity. We can do the same thing with translation, same thing with scale. So it's componentized in execution as well. But it's kind of what am I saying? Okay, there's a leaky abstraction here as well. There is an assumption that we kind of know that we have to do things in a certain way because it's going to do this. And then so this is just updating the data in the particle data container. So you've got the acceleration, everything has been updated, but we still need to parse that information and build out the render data that we're going to render, which is doing all the matrix operations. And where you do your rotation depends on, are you rotating around the local coordinate system of a particle, or around the emitter, or around something else. So when you do that rotation is in 3 different places. So at the moment there is a leaky abstraction there where the system that builds the render data from that source particle data knows what can happen. Okay, but that's an okay restriction at the moment, I think, giving us this flexibility here to change the amount of memory that we're using with each particle data container, each emitter. So now we're caught up to last week. We have working legacy components, about 90%. There's some stuff that's still missing I haven't implemented yet, but for the most part it works. And we have multiple physics components that work and are being tested a little bit by some artists. We have 2 new primitive implementations that were written in parallel to the stuff I was working on. We've got a render component with better material and shader components, so we can actually pass in an array of lifetimes into a shader, and the artist can write their shaders and have stuff pop out the other end. So that's like welcome to 2010. So we are catching up. We're getting there. So what's next? We want to flesh out missing functionality. We have a thing called Linger, which is like outro for Niagara, I think. And that's like, when the emitter dies, what happens to the particles? You might want them all to fade out, so you can kind of like override the behaviour. That's being built at the moment. UX improvements, we want it to be nice and friendly and look good. It's still a bit like, a system we have uses the data to figure out how to display it in the editor, and we can do better than that. We can make it a little bit neater, but we need to finish it first before we tidy it up. Documentation is going to be critical for this. It's going to be understandable, this particle system. So you'll be able to know that when I do this thing will happen. No more hitting things with a stick and hoping that they work. And then consultation with artists that will be using this to make sure that everything's matching what they actually want, and helping them to understand the new system and how to use it. Then we want to let engineers and artists push this system. I want engineers to build crazy new effects that do things we couldn't do before. And then we also need to profile and optimize this thing. We expect it to be slower initially, but we haven't optimized anything. But we have planned to be able to optimize. So I'm really curious to see how that fleshes out. Then what we're going to do is take all the monolithic VFX and convert them all to legacy components in data and ship to live. And hope nothing blows up. Because that's terrifying. We have systems where we can patch things that have gone out. We can roll back things if we need to. We'll be doing vast amounts of testing in internal shards to make sure that this thing is as stable as possible and that we understand the implications as far as memory and performance are concerned. But still, shipping to 100 million players will be experience. And then we get to delete all the old code. So that'll be awesome. So when refactoring big projects, understand where you're at and where you're going to and why. Code's written in a certain way for reasons. Understanding why it was written in a particular way is important. If your final goals are squishy, like we have here, design for flexibility. We need to be able to chop and change, introduce new things. But not too much flexibility. Like, don't make it infinitely extensible because it's not going to be used. Build what you need when you need it. Existing code is rarely bad. There's a reason for why it is what it is. Understand that. And like there's solution evolution. Like the problem that you designed to solve may not be the problem that's being solved 3 years down the track. Time pressure is a classic one. We've all been under time pressure to just make it work. And yeah, bad examples from those other issues will amplify and make other things worse too. So really focus on data and the functionality related to that data. The key thing with design is what's using the data, what produces the data, where does the data flow, how do we use it? All that stuff is critical. Thinking about the data means that you are also keeping code close to the data, so it provides encapsulation. So design with performance in mind, but don't try and build optimal code immediately. And just remember to breathe. Trust in your team, trust in yourself, and enjoy the ride. Thank you. We've got a microphone that we can use, so otherwise I have to repeat your question.
Thank you. This might be very obvious, but you seem very excited about it. What is SIMD?
Oh, SIMD, it's single instruction, multiple data. So it's like doing 4 float adds at the same time. So instead of adding the 4 floats independently, you can do all 4 floats in one time. It requires there's some alignment issues. There's a whole range of new instructions that you can use. Your compiler can do it, but it needs to have very strict alignment restrictions around the data that you're actually processing. So I'll be experimenting with letting the compiler do it, but I hope it doesn't because I want to write it by hand.
Thank you.
So you mentioned you've got the data silo that's holding all your stuff. So how are you reorganizing the data and how are you getting that specific parameter arrays out?
Yeah, good question. So data at the moment is just interleaved. You register each component. It says I need velocity, so I'll be using that. So at the moment you pass in an enum and it gives you can say give me the velocity component and it'll read it out for you. That's changing soon. I'm leaving it as it is now because it works, but the goal eventually is to have you will register and say I want the velocity. And it will give you back an index that'll be an array that you can iterate through and use. So you're basically, you have to, when you build a new component, you need to specify exactly what data you're using for that component. And there is a requirement on the renderer end that it needs a local transform, it needs the world transform, and it needs a couple other bits and pieces. As long as those things are created, it'll work. So whatever you do in your components doesn't matter. The renderer will still be able to pull out that information that you need. So yeah, it's interleaved at the moment, but you can also pass in structures. We can have an array of structures, or we can have just a whole lot of arrays, which is my ideal. So.
You said at the start that no plan survives contact with the enemy, and in this case, I assume the enemy is the VFX artists that are going to be using your tool, right?
Yeah, I'm the enemy to them, I think.
Yeah, exactly.
Yeah.
But at what point did you involve the VFX artists within the creation of the new, it's the workflow is so changed. I imagine that's the entire foundation for changing this in the first place, or a good part of the foundation. So at what point did they come in?
We have a few artists, tech artists that are very vocal about this, and they've been spoken to, and we are constantly having dialogue with them. They are mainly concerned with the added workflow for shaders on particles. And we've kind of, what's the word? Like, piggybacked this refactor on it because it has massive long-term benefits. So there is some workflow change, but most of the artists don't really like it anyway. So the idea is to work with them going forwards. One of the things that I want to provide is the ability to quantify the performance of an emitter before it gets into engine. So you can say, I've got these 3 components, they have a performance factor of X, add all the X's together, it gives you a number, and you can say, this is probably going to be within budget. Stuff like that we can't do at the moment, we are hoping to provide. So they're going to get a whole lot of new functionality, they're going to get slight changes in workflow. It's not too different, the actual construction process, which is why people have been using it before we've even shipped it. So, yeah. But yeah, I personally think we should be talking more to the artists, but I'm greedy, and I know how I want the code to fit. So, but the material side and the primitive side has been heavily discussed with artists, and they're working with it now and trying it out and complaining when things don't work properly. So, as is our right.
Great talk. I have a 17-part question. No, I'm kidding. So I think most people here would agree that not future-proofing is great because you don't know the problems you're going to solve later on, as you described. But I think everyone has a different interpretation of how far ahead future-proofing is. Some people might go, oh no, we should be looking at trying to account for this versus other stuff.
Yeah.
How do you define where you draw the line?
To me, my focus on this particular design has been we can add stuff if we need it. I'm not building a valet integration system that will be used by everything because we don't use it yet, so we don't need it. I'm not building a Lissajous animator thing around it because we don't need it yet. So everything that's being built is going to be used immediately. But the future proofing I suppose I've done is using this component system to allow us to chop in different bits and pieces when we need. So yeah, I'm saying don't future proof, but I'm also saying I'm planning for the future. But yeah, so it's just we need to have that flexibility in the design so we can change things when it all goes to hell, because it will. There's a guy over here who's had hand up heaps.
Oh.
Sorry.
Just while the
First.
microphone was
You
here,
go
just
first.
really quickly. You had breaking up you had creating a basic physics component.
Yep.
And then I sort of saw an arrow going to that the legacy component is inheriting from that. So
No. What I meant here is the legacy physics component has been converted into, replaced with. So that's what that was.
Okay.
So yeah, I use diagrams interchangeably. They mean what I want them to mean.
All right, that's much clearer. Thank you.
Thanks, Tony. Great talk. So migration, you mentioned at the end there, one of the next steps is going to be to take the current legacy particle systems and keep them still on the same legacy code with all the bugs that they rely on and stuff, but the new version, the modular version of it that you've got. Do you envision what's your hope or your plan for kind of the longer term future of how long you have to maintain still those legacy conversions? Can you get rid of them? Can you auto migrate, manual migrate? Yeah.
That's a good question. We actually have a system in play. Well, the evolution of our particle system has not been to this one we have now. We've got simple emitters, we've got complex emitters, and the simple emitters have been around forever, and they read off of INI files that are called Troy files for some reason. And that's been around since time immemorial, and still have a few thousand of them exist within the engine. The problem with adding in a new solution means we now have 4 different particle systems. So the goal is to remove the simple and complex as they stand at the moment completely for the legacy components. That's the first stage of that. The next stage is to optimize those. So we can go through and say 70% of the emitters only use these parameters. Let's build a component that just uses that property data and is optimized to just render that and process that, and then do an auto migration of those over to that. So we can start to push down on the memory footprint. That's what I'm hoping.
Thanks, Tony. Just a quick one. Is there any future plan to run any simulation data on the GPU rather than the CPU for the per particle?
Yeah, I've been thinking about that. We'll experiment with it, but initially we some of the stuff we're doing is starting to cause our GPU to be a bottleneck. So given our aggressive min spec, CPU it will be the initial one. I really need to think about how we can migrate to do more particle stuff on the GPU. A lot of the stuff is, the way it currently works is it's kind of, it's not really deterministic, so I don't know, yeah, we're thinking about it, but there's no direct plan to migrate everything onto the GPU, so yeah.
Great talk, by the way. Fantastic talk, especially, yeah, refactoring. Oh, sorry, close to my mouth, yep. Towards the end there, you mentioned wanting, talking about SIMD and getting really down to the metal and going, trying to get the compiler to do it, but if not, running it yourself.
Yep.
Obviously, League dropped 32-bit support 2 years ago. TFT is on multiple different architectures, and not to mention League itself is stuck on Windows. How do you work with, how do you do portability when you're working at such a low level and in doing work such as this? I'm not, I don't have any familiarity with assembly coding, but that's like the first thing that came to my mind is how do you port to mobile if you're working that close to the metal?
Mobile devices have pretty good SIMD stuff built in. So the plan would be to write a very thin abstraction layer which handles the SIMD. So we'll have our riot, multiply, add functions that we would call that would compile down to directly the SIMD instructions on each of the platforms that we have.
Makes sense.
Cool. I think that's everything. Thanks for coming.